Hello, welcome back to another episode for the Big History 2022. Today we are going to talk about one of the most important theory we have discovered is the atomic theory. Today most people understand that our world is made up of different elements. These different elements exist as an atom, and these atoms can combine to form molecules, and then there's all the material that is making up of this world. But how does this idea come from? And that is exactly what I'm going to talk about today. Let's start. At the very beginning, we were talking about conservation of mass. That is true. If the system is closed, that means there's no external things feeding things in or taking it away. So it is closed in terms of matter and energy. There's another big issue coming from the religious people. They argue that according to the thermodynamics, we shouldn't have a life here, but that is another issue we will tackle a bit later on. But anyway, in a closed system like Earth, we are on Earth, the mass of the system will remain constant over time. The mass itself cannot change even when different elements combine with other elements to form different material. Different molecules, they are still the same. That is a very old idea coming from the Greek philosophy. Nothing comes from nothing. So what exists now has always existed, and no new matter come into existence where there was none before. If we take Earth as a closed system, then we know that Earth might lose something and sometimes will gain something through the interaction with, for example, our star, the sun. The sun every now and then emits some of the solar radiation. Some of them will be captured by Earth. At the same time, all the other material coming from outer space will fall into Earth as meteoroids, and therefore we have things coming in on Earth. But at the same time, we are losing things as well through, for example, light elements flowing to the outer space of our atmosphere and then maybe blown away by solar winds. Or nowadays we are capable of sending satellites to other places, including out of the solar system. So, but in general, when we are talking about Earth here, we can safely say that nothing comes from nothing, and therefore it is impossible to create new things. We can recombine different things to form something, but we cannot create something. And at the same time, we cannot destroy something and then make it disappear. It might change into another form. For example, we have a piece of wood. We burn it, and then the wood seems to disappear. But in fact, the wood, the material, the cellulose, all the different things in the wood, eventually combine with oxygen from the atmosphere and convert into water, H2O, and carbon dioxide, etc., etc. And then it looks like we have burnt the coal, it disappears, but actually it just mixed into the atmosphere. By about 18th century, so you notice we jump very quickly from almost before the Common Era, jump right to the 18th century when people started to understand chemical reactions. That means we are able to combine different things together, and then the principle of mass is now widely used. It is a very important assumption during experiments because that is how we can study. But once we got the idea of conservation of mass, that means we can now start to quantify the reactions. For example, I have one unit of carbon which burns with, we might not know how many units of oxygen, but anyway, it will burn with some oxygen and then becomes carbon dioxide. If we are able to capture all this together, we will find that the carbon and carbon dioxide and the oxygen haven't changed its mass. So that is a very important concept. With this concept, then chemists realize that during chemical reactions, at least, substance never disappear, but only transform from one into other, always with the same weight or same mass. Here there is a difference between weight and mass. Weight is a force. For example, I have a 1 kilogram block. A block, say a wood. I have a block of wood which weighs 1 kilogram, and then this block of wood will be 1 kilogram in weight because the gravitational attraction force on this mass is what we know, so that's the weight. But the actual mass itself is 1 kilogram. So there's a slight conceptual difference here, but we are not going to touch on that at this moment. We just consider weight and mass almost the same thing, because our unit is defined in terms of the gravitational force using weight. So mass and weight, we can consider they are the same. Now with this concept of mass being conserved, that means you have X amount of reactants, then you will produce X amount of product. So the laws of conservation of mass actually is stated as total mass in a chemical reaction remains constant. Right? So that is quite straightforward. With this concept of mass, then there is obviously one very important question. We know that if you have a piece of a seed, you plant it, and then we see the plant grows. As the plant grows, it seems the plant is getting heavier and heavier, or getting more mass and mass. So the question is, where does all this mass come from? Well, the simple answer is through photosynthesis. The plant is able to take the carbon dioxide from atmosphere, water extracted from its root, plus all other essential elements. They are able to make the plant material. So the plant material actually make up of the water you put into the earth, into the soil to get the plants hydrated, and sunlight is used so that carbon dioxide from the atmosphere is being absorbed by the plant and becomes the building blocks that makes up the plant. So that is an interesting question. Here we now know the answer. With all this, then people started looking at, once we have the idea of constant mass combined to produce constant product, then we'll be able to look at what is the ratio of one element or compound react with another compound to produce the product. There is a very simple what we call simple proportion. A given chemical compound always contains its component elements in fixed ratio by mass, and does not depend on its source and method of preparation. So we have something more fundamental than the original material. For example, we have some water from the river, we have some water from the sea, we have some water from a pond, etc., etc. Water is water. It has no difference. Of course, sometimes, for example, seawater, it is salty because it has another element dissolved, the salt dissolved in the water. But if we can distill the seawater and get the pure water out, and then if we can also distill the river water and get the pure water out, then these two water is the same, no matter where you get the water. So that is one of the important concept here. And then when we talk about water, today we know that water is H2O. That means one oxygen combined with two hydrogen. But we will talk about how we discover this relationship a little bit later on. But anyway, the idea is that 1 unit of hydrogen and combined with X unit of oxygen will always produce water. And if the ratio is not correct, then you might have something in excess. And some reactions produce different products. For example, carbon. If we oxidize carbon, we burn the carbon with sufficient oxygen, then we will have carbon dioxide. But if we burn the carbon with insufficient oxygen, it will produce carbon monoxide. So we have now here, let's say we have 100 grams of carbon, and it may react with 133 grams of oxygen to produce one oxide, which is carbon monoxide. And if we have more oxygen, it will absorbs or burns out 266 grams of oxygen to produce carbon dioxide. So if we take these two ratio, 133 grams of oxygen and 266 grams of oxygen, these two ratio always produce a small whole numbers. This is very interesting. Once you started to that, we started to have carbon, although we are looking at it as a lump of black material, and the oxygen, some invisible gas. But once we come to this multiple proportion ideas, that means we can say, okay, 1 unit of carbon always either take 1 unit or in this case 1.3 units of oxygen, or you will take 2.6 units of oxygen, and that is a fixed ratio. And this fixed ratio almost mean carbon by itself can take oxygen. Oxygen exists as a unit, and that unit may be, of course, may be different in mass than carbon, but it exists a different unit. The carbon can only react either to 1 unit or to 2 units. So that is starting to break down our surrounding into small units. Now here the important question is, we want to ask the question is, suppose we have something which is which we can divide. Water, for example, we can divide water from 1 cup of water into half cup of water, and then we divide again into a quarter cup of water, and then divide again into 1/8 water again. If we keep on dividing, will there be a point where we cannot divide anymore? If our world is continuous, then we can do that indefinitely. But if the world is not continuous, if the world is made up of concrete units, then when you divide until you get 1 unit of the material, then you cannot divide anymore. And this is the idea of atomic theory. Now we are looking to see that, well, something like coal, carbon, seems to be continuous. We can divide it and divide it. Well, we cannot divide to the final carbon because it's too small. We don't have any material to divide to that level. But through this multiple proportion, we now start to get the idea. Yes, the carbon seems to like to take a certain amount of oxygen together, or another 2 units of oxygen together, because we have this law of multiple proportion, meaning that carbon takes either 1 or 2. It will not take 1 and 1.5, for example, or 1.3255, etc. It is always a simple whole number ratio. So that implies that carbon, oxygen, and etc. have the smallest unit. With this idea, then we started to look at atoms in a different way, basically starting with this chemist and physicist and meteorologist John Dalton. He also do other research. We usually accredit John Dalton with the idea of atomic theory. So let's move on to that. So in about 1803, he presented his first list of so-called relative atomic weights, because we don't know how to divide into the smallest unit. So what we can do is we assume there is the lightest unit, which is hydrogen, and then compare all the other units with the weights of hydrogen. And then it comes a very interesting observation. All the other materials always integer multiple of this fundamental unit. Of course, there are some exceptions. We know the reason why we have exceptions. For example, we now know that an element can exist in different isotopes. That means if we come down to the modern language, is that we have a element which consists of some a nucleus, the bulk of the mass, and then electron outside it. Inside the nucleus, we know there are at least two different particles, a proton and neutron. And proton determine its chemical properties. That means determine what kind of element it is. The neutron will add some weight to the, or some mass to the element. So, for example, if there is a element which have two isotopes, then these two elements, the atoms from these two elements will be, the atoms from different isotopes of this element will have the same number of protons, but different numbers of neutrons. So, but before we dig into that, one of the early findings is that all these elements, if we can find out the mass of this lightest element, then all other elements are in digital multiples. On the right hand side is a capture of some of his presentation. Obviously today all these numbers is not accurate, and some of the names in the is not elements. Some of them is actual geological names. But anyway, he started to give this idea of atoms have integer mass compared with the lightest element. At that time, he believes that oxygen, one of the most important elements, is 5.5 times heavier than hydrogen, which is obviously incorrect, because at that time he assumed the water is hydrogen and oxygen, one hydrogen, one oxygen. Of course, today we know that water is 2 hydrogen combined with 1 oxygen. And later on, he changed his mass ratio from 5.5 to 7. But in fact, it should be, if he assumed HO, then it should be 8. But if you assume the correct formula, then it will be 1 to 16. Oxygen is 16 times more heavy than hydrogen if we weight one atom of them. Then comes another scientist, Avogadro. Avogadro mainly looking at gases. He found that equal volume of all gas, no matter what kind of gas, at the same temperature and pressure, has the same number of molecules. Now, this is a very difficult concept to grasp. For those who study physics, you go into thermodynamics, then you will start to understand this. But here, he is able to say that this is very important contribution to the atomic theory in terms of that it can now look at different gases. If they have the same number of molecules, that means the unit is now standing out. It has a unit. But at that time, atoms and units, or atoms and molecules, are used quite interchangeably. But later on, we will get a little bit more accurate about what is called an atom, what is called a molecule. His law allowed him to deduce the diatomic nature of many different gases. We know that oxygen exists as a gas form as two oxygen combined together. So is nitrogen. Water exists as gas, and its combination is H2O. And there are three different elements, that three atoms to combine to form one. But it is through his study that we know all this information. One of the big problems, as I had just mentioned, he sometimes mixes up atoms and molecules, although he is now starting to give us the idea of all our existence, in our existence, every matter would comes in definite units. Then come 1827, a botanist, Robert Brown, observed that dust particles inside pollen grains floating in water constantly jiggled in what they call a Barnian motion. It is moving about, turning. It is not until 1905 when Albert Einstein is able to explain why these small particles suspended in water is behaving like this. Is because different molecules are constantly locking the grains about and produce the mathematical formula to describe this process. Okay, now go back to chemistry. By about 1750, about only 10 to 15 elements are known. If we take it even further back in time, different cultures have known different so-called elements. For example, in China, we have metal, wood, water, earth, and fire. Obviously, fire is not an element, but we say this is one of the 5 different fundamental things. Same for different cultures. They all have different numbers of so-called fundamental elements. But this number has increased ever since. By 1750, about 10 to 15, and then in the next 60 years, 30 to 40 are added to it, and then today we know approximately over 100 different elements. In 1789, one person has published a list of 33 different elements grouped into different groups. The grouping started to come in now. It is this grouping to let us understand the fundamental nature of the atom. Initially, of course, the grouping is incorrect. They just group it into gases, metals, non-metals, earth. But as the knowledge increased, then we started to have more and more understanding of how all these different elements are grouped together. The next one comes with about 1817 with the law of triads. a scientist, I can't pronounce his name anyway. If he try to arrange the all the different elements by its known weights, then if the elements have similar chemical properties, then if we arrange these elements at three of them, three different kinds of elements have approximately same weight, then it it's not a different weight, okay, and he can actually find out that the middle one is the average of the first and the last. So this is known as the law of triads. And then eventually we have a number of these triads. Here are some examples here. For alkaline metals, I'm using today's terminology for all these elements. Lithium, sodium, and potassium. They are all alkaline metals. So if we add the weight of lithium and then add the weight of potassium, so 7 plus 39, and then divide by 2, we get 23, which is exactly the mass of sodium. So he is able to find this very interesting relationship. With this relationship, then we started to group them in different ways. One way to group them together is obviously through these triads. Another way to group them is all arranged in this in a line, and then all those in the same with the same properties, chemical properties, is on as a column. So we are starting to build what we today know as the periodic table. The first one to crack this is John Newland. He arranged the elements in order of their atomic mass, and notice that there is a repetition every 8 elements. The obvious one is the blue one here, barium, magnesium, calcium, and then strontium. The yellow color were something they don't know at the time. They can see the vertical, for example, lithium, sodium, potassium, which is the first known triad. And then we have, for example, fluorine, chlorine, and bromine. The nickel is missing from the original plan. The yellow ones are originally missing, but he was able to just put it there, stuck there, and then we will see a similar patterns. The blue one had the similar chemical properties. The light blue ones had similar chemical properties. The yellow one had similar properties, etc., etc. So we started to have this initial so-called periodic table. Of course, the periodic table get revised, especially when another concept called valency in chemistry is known, and that talk about how many other atoms one atom can combine with. So that's the valency idea, and then eventually moving on. So we are not going to touch into all these details now. We know that at that time some missing, and therefore people are able to actually predict what is missing, and that is the important thing about scientific theory. The scientific theory is able to predict, and then with that prediction, then people can start looking for that particular element. So this is now the current periodic table. Most students in secondary school will have to memorize at least the first 3 rows. The sequence being hydrogen, helium, lithium, barium, boron, carbon, nitrogen, oxygen, fluoride, neon, now sodium, magnesium, aluminum, silica, phosphorus, sulfur, chloride, and argon gas, and so on. Most students will be able to memorize the first 3 rows. There are other elements which is commonly found, but it can't fit into these 3 rows. For example, iron, Fe, with atomic number 26. But anyway, This table now becomes a very important idea we will be talking about next. Another way to draw the periodic table is like a spiral. Okay, so every finger will mean similar things in the same manner. So there are different methods of representing all the elements. With this, then we started to understand, okay, from the chemical properties direction, we know that there is a smallest unit which will combine with other smallest unit to produce different molecules. So we don't know what that unit is. A lot of people assume, oh, that must be a sphere or something. Okay. But physics now comes in with a big problem. When physicists started to find out electric charge, initially they understand this as electrostatic charge. For example, when we rub some rubber against some fur, then we'll be able to use the rubber to attract small pieces of paper, and we call that static electricity. And that static electricity leads to understanding of electric current. And with electric current, people are starting to try to understand what is a current, what does it mean. So actually, the definition is the wrong one, and therefore today we have electrons being negative, and electron is those things which is flowing mainly. This comes with a so-called cathode ray tube. On one end, we have a hot cathode, and that cathode, hot meaning that it will be able to release its electrons much easier because it's hot. The atoms will have high energy, and with high energy, you will be able to put a positive field, a positive electric potential to attract the electron to come out. As electron come out, it will travel from one end to the other end, and then it will hit on a forensic material on the other end, so we can see the electrons striking at some places. So one initial experiments, of course, is to put a different electric charge on a plate in between the path, which is in the middle of this diagram, and then we can deflect the current, the electrons, and we find that the electrons are being attracted towards the positive side of the flow of the electrode. So we now coming with something quite different. It is outside chemistry. We know that material can produce static charge, and static charge can move through a vacuum. And with this is one of the schematic of the cathode ray tube before. So on the left hand side, we have a hot negative area with a positive gate, which is a mesh attracting electron coming out, and then passing through a small hole, which is earthed, and then pass through two electrodes. In this case, a positive lower in the yellow region, okay, the negative in the upper region, and then you will strike on a different spot. Then he suggested, okay, atoms are actually divisible. It has a positive and negative things in it. A negative is called electrons. The positive is the remain of the atoms, and they must be neutral. Normally, it's neutral. So we have this so-called the pudding model. That means an atom is look like a pudding, a bulk of material, and then on top of it there are electrons sticking into this positive middle part. So it was the Thomson's atomic model. But soon his model is overthrown by an experiment from his student Rutherford. Rutherford at that time had been playing with radioactivity. One radioactivity, we know that it's a very heavy positive radiation. We call it the alpha ray. And Rutherford shined the alpha ray through a thin foil of gold. Now, if it is the Thomson's model, we'll expect all the alpha particles will just pass through this pudding, or maybe some of them will be absorbed by the pudding, but it will just pass through. But the experiment comes out that the alpha particle, a lot of them just pass right through, but there are a few which actually get the bounce back even almost more than 90 degrees bounce back, as observed in the lower right diagram. How to explain that? So he had to change the Thomson's model from a pudding into a new model where the bulk of the atom's mass is in the center, what we now know as the nucleus. Nucleus is positive, and electrons are moving around this positive nucleus. This is the Rutherford experiment, and then he had to propose that there is a planetary model in which a cloud of electrons surrounding a small compact nucleus of positive charge. But there is a big problem here. We at that time is already know that when a electron is being accelerated, moving around a nucleus is being accelerated all the time, then it will radiate energy. If it radiates energy, that means the electrons will very quickly lose its energy. That means it's kinetic energy, meaning its speed. As the speed lowers, then it go closer and closer into the nucleus and eventually get into the nucleus. So this model doesn't stood up to the classical model of physics. We have to move into the next model, which is the quantum model. In the quantum model, it is hypothesis that if the electron is moving in a certain specific method around the nucleus, then it will not lose its energy, because energy has to be lost in what we call quantum. That means we lost 1 unit of energy. We cannot lose half a unit energy. When we lost energy, it must be 1 unit. That is the quantum theory. So it was Planck, Einstein, Bohr, a number of physicists working at that time eventually produced this quantum theory. Another interesting thing in terms of history science, Albert Einstein has for a long time struggled with this idea of quantum. He actually have a long debate with Niels Bohr, and their debate is a very interesting debate for those who are interested in the early stages of quantum mechanics. Another interesting observation is that, again, this is known for a long time. We have a gas, and then if we pass a large current on it, then the gas will grow, will produce light. And if we put the light through a dispersion method, for example, we know that if light passes through a prism, it will separate into different color. So if we have a elements, heat the element into a high temperature and let the light coming from this element pass through something like a prism, then you will separate out into very discrete lines. We call that atomic spectrum. And the atomic spectrum is unique for different elements. The diagram here is the halogen spectrum. Today we know that the halogen spectrum is because the electron is jumping from one level to the other levels. The ground state is n equal 1, and then it has different ground state. When it heat up, it come from the infinity, some will jump to different places. So we have different lights coming out from that one. So in order to explain this, okay, these are two different spectrum from two different elements. In order to explain this, I think it's either Bohr use the first quantum model of atom, explain all this, why this light come from. We take a long time to come to this, talking about atomic theory. Why? Well, because if we want to understand the universe, we cannot go outside of Earth. We cannot go to other galaxy or other places. What we can do is only through observation, by looking. This is the only way we can know anything outside of the Earth. And therefore, understanding how light can come out from objects give us a way to understanding what are the materials in the rest of the universe. And therefore, we spend quite a bit of time to describe this atomic theory. This is a bit long, and I hope you come to this very last stage. And if you think this is useful to you, please subscribe and share this video with your friends. Thank you. Bye-bye.